If you're not familiar with the pulsed laser deposition in detail, I will shortly explain this technique to you. So we have here a typical setup where we couple our laser pulse of wavelength 284 nanometers, so in the UV range, and a pulse length of 30 nanoseconds. We couple it via a lens here that's rotatable, couple it in here to a UHV chamber. The base pressure can be up to the 10 to the minus 9, but this is only for chamber number 3. The other chambers are 10 to the 6 to 10 to the 8 millibar before deposition. In the chamber here, the laser beam is focused onto a target. In the chambers we can have multiple targets at a time, so you can deposit multi-layers. The targets are moved, mostly rotated, but with chamber 1 it's only a moving procedure installed that tries to avoid the roughening of the target. Here at the target site, the laser beam heats up the target to a few thousand degrees C, and the material is instantaneously evaporated. This material that's then here directly above that target is then further ionized by the incoming laser beam, and a plasma is generated that is expanding directly rectangular here to the substrate side. Here we have the possibility to heat the substrate in chamber 1 and 2, and it's also moved, so we have a homogeneous coverage, since here you see this plasma plume has a very directed shape here. Of course, when you introduce a background pressure, you can also tune the shape of this plasma plume a little, but in principle you will have here a cosine function of thickness gradient, and when moving or rotating the substrate you can smoothen this out and homogenize your layer thickness. The repetition rate of the laser is up to 10 Hz, and the maximum power per shot or per pulse is up to 600 millijoule when the laser is freshly filled, so you can reach fluences or energy densities up to 25 joule per square centimeter. What is interesting with this pulsed laser deposition is that you can apply this technique to any kinds of materials. So the main focus in the 80s was on high temperature superconductors. There this technique became very famous, but also oxides, nitrides, carbides, semiconductors, metals for sure, but also other things like halides, polymers and fullerenes can be deposited using this technique. Here we have also the tremendous advantage that we have the deposition source, so the laser, it's outside the chamber itself, so you don't have any back coupling like it is in sputtering techniques from the actual deposition process to your source. And this is why you can have such a variety of different materials. I'd now like to show you the most recent results that were fabricated with the different chambers. So here we have the tin-based halide perovskite. They were deposited in chamber 3. It's a collaboration within the Institute of Materials Physics, and also Toby Meyer, who is part of this lab tour, contributed using the transmission electron microscope. The next example for the complex oxide growth is here a collaboration with Vasily, you also know from this lab tour, and the group of Christian Joos here from the Institute of Materials Physics. And there we grew epitaxial Rudelston-Popper PCMO films, and this is the first paper on growing thin films on this material. And last but not least, here an example for the multilayer deposition that was done in chamber number 3. This is a collaboration of the Institute of Materials Physics and the Institute of X-ray Physics. Here we deposited by pulse laser deposition a multi-layer zone plate as an X-ray optic. I will show you here the procedure. On a rotating wire the PLD was performed, and here we have the material system, tungsten and silicon, that was alternately deposited on that wire, and the so-called zones here, those circular rings, they have to be thinnest at the most outside position here, and there only a few nanometers are reached, and the homogeneity and the precision of those layers, they are responsible then for the resolution of this optical component. And here in this paper we reached focusing in 2 dimensions of below 5 nanometers. That is, at least to my knowledge, still the record for hard X-ray focusing. So this precision can be reached using the PLD setup. If you don't have access to that papers and want to have a look at it, I'm author, or at least co-author, so feel free to contact me. Thanks for your attention.